All right. So let's try this again. Where were we? We were, nope, here. All right, so on Friday, we'd been talking about an oil spill, how much had spilled cumulatively starting from time 0, the time when the oil started leaking. And you can maybe kind of imagine what the graph looks like, but it's really hard to figure out Y values, like how much, like how high is this actually going? How steep is steeper than another part? Like you can say, oh, well, it's leaking faster at first and then more slowly later on, but we really need to, if you want to sketch this, assign some values at some point in time so we can get a reasonable graph that has some approximate correct Y values, meaning cubic meters of oil that had leaked. So what we talked about is, first of all, whenever you're looking at graphs, we're going to see two different sorts of things graphed now. Most of what you're used to seeing is a graph of how much of something there is, whether it's a graph of area or distance or something like that. But what we're going to be looking at is graphs of rates for the next while here. So the rate at which the oil was leaking. And then so meaning the dependent variable values, the vertical value aspect of this is telling us how fast something's happening or how quickly something is changing. It doesn't always have to do with time, but how fast one thing is changing relative to another. In this case, it is how much oil is spilled with respect to, or at what rate the oil is leaking with respect to time, so meters cubed per day. And we said that if you actually have a constant rate, like that bathtub graph we looked at the start of class on Friday, an exactly constant rate, if you're looking at the rate graph, would have one Y value, one dependent variable value throughout. That the dependent variable isn't actually varying, not meaning that it's not a variable, just it's the sort of function that's a constant valued function. So in any case, this is not exactly horizontal, but zoomed in, it doesn't drop a whole lot from left to right. So it's near constant, and all these values right around time 0.7 days. So this is a moment around 0.7 days, where the rate from left to right in this whole moment clearly does change from closer to 9.8 to closer to 9.6, but especially right around 0.7, you can imagine this rate that's right around maybe 9.7 cubic meters per day of oil that are leaking. Now, again, this 9.7 cubic meters per day doesn't mean that after a day 9.7 cubic meters will have leaked, because we know this rate is changing all the time. But if we think about a small amount of time, in a small amount of time, the amount of oil that leaks is going to be 9.7 times that amount of time measured in days. And we measure the amount that's leaked in terms of cubic meters. So what we talked about at the end here was like, well, and let me scoot this again. If I want to find the volume of oil that's leaked by time 0.7013, if I have a value that's quite near there, 13.15, what we talked about was, and let's see if I can do this without messing up everything. So at time 0.7, we have this 13.15 cubic meters of oil that had leaked. And over the next 0.013 days, so up to, let's see, that's that's 15, so a little bit to the left of that. 0.7013 is maybe the left of those. Maybe I can, here. There we go. Does work not too horribly. So I want to be increasing at a rate where the vertical change is 9.68 times this amount of horizontal change. If this is my dx value here, I want my dy to be 9.68 times that. For any amount of change in time that's small, when we're talking about not entirely constant rates of change, for any amount of change in time, my change in volume is going to be 9.68 times as much. I'm just going to make sure to only pick small amounts of time so I stay within my moment where this rate seems a reasonable rate to use. So the vertical change then we came up with by the end of class, what was this for 7.7013, the dy value rather? It's this 9.68 times 0.0013. And we came up with a value. What was that? 13.15? 13.15. Now this is not what the volume of oil is that's leaked. Oh, that's the new 13.15 and then plus 9.68 times 0.0013. What does that add to? All right, so 0.1626 to get the new y value. So 0.1626 is the 9.68 dx, and then adding that on there, we get 13 point, what, 6?
We got 13.166.
Oh, sorry, 13.1626. All right, so this is 0.0126. All right, so 0.0126 is the dy value, and then we got this 13.1626 as the new value of y, the y final after an incremental increase in dx, or in the x value rather, by this dx value of 0.0013. So the second part to the question was, well, what if I wanted to find the value of the volume of oil spilled by time 0.702 days? Slightly larger, right? 0.702. You can do this a couple of different ways. You should get the same result. You could start from this point that you just calculated and increase by an additional 0.0007. No, 0.0007, right? Or you could again use the same initial value and increase by 0.002. You should get the same result if you're using the same constant rate, this 9.68 cubic meters per day, right? Because whether I start from time 0.7 and go forward 0.002 at that rate, or whether I stop in the middle and then restart again, as long as I'm using the same rate again, I should get the same final result. It's an additional, in this picture, it'd be an additional, let's see, 0.007 that way. Oops, I passed point. And then the vertical change, 9.68 times as much. So 9.68 times 0.0007, or 9.68 times the original amount if you use this kind of like larger triangle. As I said, a couple ways you could do this. But there's two different things we can find here. We can find over this small interval of time the amount of change in the amount of oil that's spilled, or since we have a starting value for how much had been spilled at one particular point in time, we can also calculate now what's the new total. Add that onto the old total to get the new total, adding the y initial plus dy, y initial plus mdx, to get that value by time 0.702. What is the new y value by time 0.702? Or in other words, what's v of 0.702 come out to be? 13.17? We agree with that, maybe? Yeah, it's not a whole lot larger because it's not a whole lot more extra time. I don't know what 7/1000ths of a day is, but it's not a whole lot of time. So in any case, in that extra 7/1000ths of a day, still increasing by 9.68 cubic meters per day is not a whole lot of increase overall. So looks like about 3/4 of a hundredth, whatever that would be. So the units on these are cubic meters, and this is cumulative cubic meters that have been spilled by 0.702 days into this. Now, the problem we run into is that this is kind of tedious. As you can see, there's a lot of little computations. So what we'd like to be able to do, instead of picking a lot of random times and needing to know something really nearby, is to have a way to start from the beginning, whatever the beginning is, in this case when the oil started spilling, and maybe make a regulated sort of every so often. I'm going to measure a rate, kind of like we did down here at time 0.7 days, but every so often I'm going to measure a rate like that and use it for a small amount of time and generate from that a pattern of increasing amount of accumulated oil in this case, or it could be something that decreases if I had negative rates in another situation. By the way, if I had something that was a negative rate, something like a rate of decreasing by 2 cubic meters per hour, something draining away. If I were looking at a graph of my rate function, realize that that would be negative y values. Not necessarily exactly constant, but in small intervals, I'd have negative y values that stayed relatively the same. So I could have, in other situations, not this one, negative rates. In this one, I have positive rates. It's oil spilling. It's not going to unspill. But let me clear this off. And go with this. All right. So just to kind of summarize then, if I have a graph, right, the graph on the left here, the red graph, the rate of change of oil entering the ocean, leaking out of the ship, at any number of days after the leak began, and on the right I have the accumulated volume of oil leaked at any number of days after the leak began. The relationship, again, between these two things, even though it's not exactly constant rate of change throughout this multiple number of days, if I look at small moments at a time, we can use our same tools that we used during our first unit before the first test with constant rate of change and the multiplicative relationship that we had there. Meaning, regardless of exactly how this rate of change is, except at maybe a few moments in weird cases where there's not an essentially constant rate of change at a moment, like the point of an absolute value graph, like we looked at one day, I can use this constant rate of change. In this case, we have m, the m of dy equals m dx, measured in cubic meters per day. And we can find changes in the volume. What was the top half of the rate? The cubic meters. So the equivalent of the dy in our generic form of this, dy equals m dx. Here's our dv. The changes in volume, small ones, are multiples of small changes in time. Differentials in time multiplied by the constant rate m that applies at the moment gives us the associated change in volume. So from that, and this is what we did on the last page, in addition to this like dy equals m dx, part of our constant rate of change, dependent variable differential is a multiple of the independent variable's differential. We can also find, if we have an initial value to start with, whether it's at the beginning in this case, we could think of an oil starting to leak at time 0, there's 0 oil leaked. It's not always the case that we start from 0. But if we have an initial value that we know something about that we can start from, we can talk about adding changes in that to get new later values. And so that's how we could progress from the origin here, representing the oil leak starting, saying, well, after a little bit, the volume's changed by a small amount. Now it's not 9.68 times as much here. We've got different rates. Near the beginning of this graph, there's somewhere between 25 and 30 look like the rates in cubic meters per day. So if I wanted to estimate how far up this goes, meaning how much oil had leaked in the first little bit, I'd need to do some sort of computation. So that's what we're going to do next. We're going to let's look at this as a whole. The same principle applies throughout. I'm going to make an approximate, I'm going to pick some approximate values to use, or values of this rate function. I'm going to pretend that they apply for a little bit longer than they actually do, so that I can get a reasonable approximation that will actually, in the end up being not too bad, considering how bad our approximation is going to look. So the idea is, if we can find a constant rate, then we can find the change in the dependent variable that goes with it over a small interval. And then from that, find a new value of our dependent variable that we can work forward from there. So we're going to do this a piece at a time, because as we go through this, I can see, well, at the beginning I'd like to use higher rates. Later on, I'd like to use lower rates and lower and lower. So I can't use one rate throughout because this changes significantly. I'd have a really bad estimate if I used like 28 cubic meters per day for 2 whole days. That wouldn't be very much what's going on. 28 is about where this is. And this rate isn't too close to being 28 all along. But it's close to 28 maybe right here, and then after a bit maybe closer to 23 or 20, or I can pick some other numbers and use them later. But this would require that I construct the accumulation one piece at a time. So we're going to make a piecewise function both for the rate to describe how we're going to choose these rate values or rate functions, and then make accumulation that corresponds to that approximate rate that we chose. So let's say that I want to use that first rate value. Like I said, it looks like it's maybe about a rate of 28 cubic meters per day just looking at it. I could call it R sub V of 0, but just to have a number to work with for a minute, let's say that I'm going to say that this R sub V of 0, the Y value at where this dot is here, maybe it's about 28. Just looking at it, cubic meters per day. So let's say I do that. I use that rate just for a little bit. Now, at the beginning, for the first, 0.003 or so of a day, that's a really good estimation. By the time, and this is just the first 0.3 units, so up to 0.3. For the first 0.3 units, the first little bit, it's good, and then it gets worse and worse as time goes on. So we'll readjust and use another rate later on. So at time 0.3, let's pick a new rate. I just picked 0.3 because it's kind of convenient, not too hard to use, as opposed to picking 0.0015 or something really small. I'm picking something that is big enough for you to be able to see it and see multiple days here, but small enough so that it's not going to give us a horrible, horrible estimate. This looks bad though, because by the end of these 0.3 days at a time, the approximated rate function is significantly above the actual rate function. And what I mean by approximated rate function is I'm making a new function out of the red curve that was there. Now this is called a step function. It's piecewise constant. But looking at this, I can say, well, let's see. This height here looks to be about 20, so I'll just use 20 as it's a nice round number as an approximation. The exact value is the value of the red curve at time 0.3. So exactly it's R sub V of 0.3 days, approximately, so that we can do something with it, calculation-wise. Let's say it's about 20. So looking at the next ones, again, I could say this is R sub V of 0.6, and it looks like it's about 12 or so. And then I'm up to 0.9. So every 0.3 units, to make it nice and even, easy to count, easy to figure out where I am if I do this, not just pick them based on what the picture looks like, but every 0.3 days, every 3/10 of a day, we're picking a new rate function to use, or a new rate value rather, to use. R sub V of 0.9. Or about, let's see, what does that look like? It's a little bit above 5, so let's call it 6. And then this one right here, which this is a very good approximation. Over this interval that runs from 1.2 to 1.5, that segment is, from this level of zoomed in, it looks like it's very accurate. And that height is maybe about 3. So I'll call this R sub, oops, not 0. R sub 1.2, R sub V of 1.2 rather, looks to be about 3, about half as close to the, or twice as close to the x-axis as the last one. So this is a function that we could define, write it out, its function rule exactly using that function notation R sub V, the rate of change of function V, rate of change of the volume of oil, just by using this function notation. But it's the blue lines are definitely a different function from the red curve, agreed? They're not the same thing. But the blue is meant to approximate the red curve there. It's a kind of poor approximation except for this last interval, in which case it's pretty close. But regardless, it's actually close enough so that we can get a good estimate of how much oil is spilled. And in terms of estimating, if you want to estimate how much oil is spilled and report it to somebody, you'd probably rather have an overestimate than an underestimate. This would be overestimating because the rates are most of the time above the red curve, the blue approximate rates that we're using here. So I'm going to call this function R, just plain R, no subscript. So this plain R here is representing the approximate rate function. Because we're using one single value of the actual rate function at a time. So we use one single value more than just at time 0. We use it all the way up to time 0.3. Well, almost up to time 0.3. At time 3, 0.3 rather, we pick a new value that was about 20, and we use that for a little while. So this piecewise function again, these t values here, those are the values of time. Each one of those lists an interval or domain during which we use these. Now this isn't particularly useful for us to look at for calculating purposes, but if function capital R sub v was defined, some weird, ugly polynomial, if you defined it in GC and gave GC this piecewise function, it would know exactly what all those are exactly, as opposed to decimal approximations to a few places. So this would be a nice way to define this approximate rate function. And this just, I did these first few sections here. We could keep going, but 5 pieces of this would allow us to figure out how much oil had leaked over the first day and a half, up to time 1.5. It would be an approximation, and it would be a slight over approximation. But again, just a couple of things about this. A, we constructed a piecewise function. B, the notation. The exact rate of change function was R with a subscript of V. The approximate rate function, and we'll do this for all of ours. When we're making an approximate rate function or trying to talk about an approximate rate function, we'll just call it R. We're going to use it just for discussion, but notice that R only requires that we know a subset of the values, a discrete number of points, or at least set out evenly spaced points, values on the rate function, as opposed to all infinitely many between 0 and 1.5. We're using 5 points between 0 and 1.5. We're using those 5 points dependent variable values. There are many, many others which we're ignoring, but if I wanted to graph the accumulation that happens here, that's when it might be useful to think about the number. So just approximating our approximation. So we have an approximate rate function, and then there's these approximate values that we're using also. So this 28, I just kind of made up 28 because it's between 27.5 and 30. But if I say that this rate is 28 cubic meters per day, and I'm going to use this for the first 0.3 days, I can imagine, all right, well, our oil spill starts from nothing spilled, and we know that we're going to increase any horizontal amount of change that we have between 0 and 0.3, which is right there, is going to happen at a rate where the vertical change on this graph is going to be 28 times as much as the horizontal change. Now this is scaled, so it's not going to be off the top. So this isn't 0.3 in the other direction. But if I move to the right by 0.3 units, if I go across this whole interval where I'm using this constant rate that was generated from the actual rate at 0, the vertical change would be, let's see, dV would be mdx. 0.3 is the dx part, and our rate we're using is 28. So this is, sorry I wrote this kind of in backwards order, but that's the m, and this is the, well, dx or dt. I guess t was the variable for the independent axis. So 28 times 0.3. That would tell us if I go all the way across from 0 to 0.3 days, my volume of oil would increase from 0 to 8.4. All right, so 0 to 8.4, and 8.4 is, estimating-wise, here. Now, this is an equation, so we're going to eventually generate an equation for this line, not just for the value at the end point. But this endpoint here is 0.3, 8.4. which is good to know because if I want to generate or use my next increment between 0.3 and 0.6, the next 0.3 units, I'm going to be using a different rate. If I want to graph this, I'm going to need to know where my graph starts from. It starts from that point at the end there and then goes upward at a different rate, a rate of only 20 times the change in x, or t in this case. So for the second interval, if I go all the way across that 0.3 days, I'd increase by, vertically, by 20 times as much, 20 times 0.3, which is 6, instead of 8.4 that we got the last time. So going up 6 from 8.4, well, my new, so this one was easy. I was starting from 0 and going up 8.4. Now I'm starting from 8.4 and going up by 6, 14.4. But you have to actually do some adding. So 14.4 is about there. So the second line segment here would be not as steep as the first one. I'm going to write this point up here so it's out of the way. But at 0.6, the volume of oil that had been spilled in our approximation would be 14.4. Which, this is the dV to get the new value of V, V initial plus dV. I don't want to go back to 0 and add on 6 because this isn't the rate that applied from 0 to 0.3. It's the rate for the second section. So we append it on. Or over the first interval, we had a dx, or dt rather than dV. Then we have another dx with a different dV ratio. And then we could go on. But you'll see on your graph you have an expression that started there for a piecewise function called a of x. This a of x is the approximate accumulation, or a of t rather it should be, approximate accumulation by time t. But just to think about the first couple parts of this, if I want to write this as a function, I don't just want the endpoints. I want to say if t is between 0 and 0.3, I want to be able to write an equation for this whole line segment where as long as my t is within this value, it'll put me at the appropriate dependent value, the amount of accumulated oil that had spilled. Here, let me rewrite that. A of t. But this is our accumulated approximate oil spilled. So in total since time 0. But this equation here, I know the rate. I need a y initial plus mdx. Well, we're starting from 0. So the first segment, just like when we were drawing it, was kind of easier. We're just starting from 0 and going up at a rate of approximately 28 per t. So I could say, oh, it's about 28 t. 0 plus 28 t. If t is between here and there. So this is our m and our dx. That one was kind of the easier one. Now, for sections past that, besides the fact this 28 was an approximation of my approximate rate, exactly I could call that r sub v of 0. For my next section, between 0.3 and 0.6, I'm going to use a different rate for sure, right? It's about 20. But I need my y initial, which was about 8.4. Again, this is an approximation. Plus, so this is y initial plus mdx sort of writing. Here's my initial value, 8.4, which is where we were at time 0.3, plus mdx. So again, it's a two levels of approximation here. Now, 20, it's not just 20x here, because I'm not increasing using this rate of 20 all the way from the beginning. The dV that we calculated was only based on, to get up to this point 14.4, that's based on being 0.3 units away from here. 0.3 units away to the right of t equals 0.3. Well, in general, I don't have to go all the way across. I want to know not how far I am from 0, but how far I am from 0.3. T, or t minus 0, is how far you are from 0. If I want to know how far I've moved away from the beginning of this interval, dt, x final, or t final minus t initial. If I'm in this interval, the beginning of the interval is 0.3. But to describe this line segment that I've got here, I'm putting in more numbers here instead of symbols to represent these, just so we can see how we're computing this. But we started at that height 8.4 that we ended with the first interval at. By the way, if I sub in t equals 0.3 to this, I get 8.4. That's what we did. But at that point, we started using a new rate to go forward, so that's why I have the or equal to is kind of where they are. In any case, if t is 0.3 or larger, I'm going to use this expression. Well, not or larger indefinitely, but or a little bit larger. I start at 8.4 and then increase at a rate of 20 y's per x, or 20 volume per time, for any amount of time I am past the starting position. The starting position wasn't 0, though. The starting position at this rate is 0.3. Or if we want to do a third section here, using this rate of about 12 from 0.6 to 0.9, well, however far I go across, if I want to go all the way across this section, I'm going to have this change in volume as all the way across the section times my rate of 12. 0.3 times 12 is 3.6. So add an extra 3.6 onto 14.4, and we should get 18. Which I think I have that in about the right spot. So this graph, we've only done the first 0.9 days. I'm going to write the function that goes with that third segment in a little bit. But we increased first quickly, and then more slowly, and then more slowly. If I were to split this up and do this every 1/10 of a day instead of 3/10 of a day, it would be possible. It would be a lot more tedious. For doing this by hand, that's why I chose 0.3 days at a time, even though this is not an extremely close approximation, so we can kind of see what's going on. But if you see the shape of this graph that's forming here, it doesn't look extremely different from the blue curve that we saw that was the exact rate of change. Went up and over. And because the rates of change over these small intervals are so similar to one another, it's almost hard to tell that they aren't a curve, even though they're definitely not. I mean, my poor drawing doesn't assist any. But going up at 3 different rates here, first at a rate of about 28, then 20, then 12, we get this thing that, if you kind of blur your eyes out a little bit, it looks kind of like a curve. And it looks very close to the curve that we had. Now, it's a slight overestimate of where the actual curve would be. If I draw these lines a little bit fatter, it'd probably not be over anymore. But just for this last section, I know I'm starting at, for the third section, and there's actually 5 of them here, but if I think, here's my x initial, y initial. If I want to write an equation, if you remember the constructing wooden tables question on your test, you had a point kind of out in the middle of nowhere, and you're supposed to increase towards some generic xy at a given rate of 26 hours per table or something. Well, here's our point out in the middle of nowhere. 0.6 comma 14.4. I know I'm going to end up here eventually, but starting at 14.4, I'm increasing at a rate of 12 cubic meters per day. How far am I across? Well, I'm in this third interval, so I measure how far I've traveled at that rate by how far I am from my x initial there, from 0.6. So it's not x, it's t really, minus 0.6. So I have this written out much more neatly, but this would apply from 0.6 to 0.9. This is the numerical version of this, using my approximate values of 28, and then the y values, 28, 20, 12, etc., and then the y values that go with those that we calculated, so we can have a chance of graphing this. But let's take a look at what this would be if we do this, using more notation, harder to calculate with, but to say this approximation precisely, it's kind of easier to see the patterns instead of worrying about, wait, was it 14.4 or was it 17 or 18 or 0.0003 or what sort of numbers. If you can take some of the numbers out of it but know what's going on, we've got two main things that we're doing here. If I want to write this accumulation function, and again, this is approximate net accumulation. Now, net accumulation means start from 0, just measure what changes happen past that, or start from whatever the given point is. This, our oil spill started at 0, we're measuring oil since time 0. So for the first 0.3 days, and this is space here because I need more space for some of the others, I just use my rate, which we said was about 28, times how far I am past 0, which is t minus 0 is obviously just t. But this was our 28. Let's see, here we go. This was 28 when we were doing our approximation, only because we said, oh, between 0 and 3. So I just have r sub t here, which is this whole function. The whole purpose of writing this wasn't just for exercises. I can refer to it. When I'm between 0 and 0.3 in time, r sub v of 0, or this number that's about 28, is the value of r of t. So I don't have to call it r sub v of 0, and I don't have to call it 28. I can just call it r of t, because if I'm in this first interval, that means those all mean the same thing, where the 28 was the approximate value of it, just based on looking at it. We don't have a function rule listed anywhere. Between 0.3 and 0.6, we have that same sort of thing. So this red here, this is our, now let me change the red. The red part here is our rate, and then how long we use that rate for. So this is our mdx sort of expression. Let me actually write that. When I'm in this first interval, this is the mdx, the rate and how long we use it for. If t was 0.1, I could use this formula, sub in 0.1 for t, and then I'd know I'd be using this rate of 28. Do 28 times 0.1 and get 2.8. For any value of t between 0 and 0.3, not just the beginning and the end, this rule applies. I use that rate, that's the first rate, about 28, for that interval. In the next interval over, we'd use this rate that's about 20. When I'm in the second line, this r sub t now has a value that's about 20. And this is my, again, mdx sort of expression. This here that I have in blue, that's the y initial plus mdx. So where did we start from? Oh, we started from, well, having used that rate at 0, either r of 0 or r sub v of 0, they're the same thing. R of 0 just means, oh, t is 0, I'm using r sub v of 0, which is still 28. But this is that, use the rate of 28 for the whole 0.3 seconds, so that's that 8.4 number that we had before, or not 0.3 seconds, 0.3 days. So this is our 8.4. The first one, we don't have that y initial because we were starting at 0. If you wanted to write that for the first line, we could have 0 plus that 28 times t minus 0, or whatever. But we don't usually have to write 0 plus, just like you don't have to write minus 0 here, kind of a extra notation. The reason I wrote it, though, is so that you can kind of see what the pattern is. So the third one, this looks the messiest so far. That's the one that we just did. If I want to write this symbolically as opposed to using numerical approximations, I still got that mdx, that r of t times t minus something. T minus something tells you how far t is past that something. If I want to know a value of dt, like dx in the generic form, I need to compare it to a starting position. So when I'm in the interval between 0.6 and 0.9, how far am I into that interval? Oh, subtract 0.6 from it. So if my value is 0.8, dt is 0.2. If my value is 0.3, 0.87, then this would be 0.27. So I can find the corresponding dV value, or the MDX value, from doing my constant rate that I'm using for that interval times how far I am past the beginning of the interval. Now, all this stuff in blue gives me my y initial. If you can see, this is the same as the previous line, r of 0 times 0.3. That's where I was at the end of the first interval. That's the y value at the end of the first interval. This is the accumulation that happens during the second interval. So I have all of the oil that spills during the first interval, plus all of the oil that spills during the second interval, plus what's spilling while I'm in the third interval, between time 0.6 and 0.9. So the ones that are in blue here are completed. We're already past those. Those have to do with earlier rates that we're no longer using. Or these parts here are constants. So as t gets larger and larger, I have more constants that I've already passed. Oil has already spilled. Now I'm spilling at the new rate, which I can refer to over here. And as I go on, that constant part, the already accumulated oil that spilled at earlier rates that we're no longer using, we already used them for the full 0.3 days, that's all done. So it gets messier and messier, that part. The initial value starts at 0. And then when we're in the second interval, we have 1 full interval's worth of oil accumulation. When we're into the third interval, using this rate that's around 12 or so, there's oil that spilled at 2 different rates earlier that's already sitting there, well, floating there, whatever it's doing. It's already spilled, and now we're spilling at a new rate. While time is between 0.6 and 0.9, I'm using this new rate that's somewhere like 1.2. When I'm done going all the way through that interval, once I'm all the way to 0.9, then I've got this extra amount accumulated. So the stuff in blue represents, vertically speaking here, let's see. The height here we said was about 8.44. So the volume after the first interval, I'll call it V1. The volume after the first interval is this high. After 2 intervals, we're at 14.4. So the volume after 2 full intervals, after 0.6 days, was up to there. After 3 days, it was at 18. There's an extra something that, let's see, 3.6. But this is V1. V2 is the sum of those two. V3 is the sum of those 3, because those are all the y values depending, like a full interval's worth of accumulated oil. They add on to one another. Now, where they happen left to right, the first one happened between 0 and 0.3. The next happened between 0 and 0.3 and 0.6. So I got up to this second full interval's worth, 0.6 days worth of oil, by adding this change in volume in the second interval onto what we had at the end of the first interval. And then we changed again at a different rate. We ended up at, by 0.9, we were at height 18. Going up at slower and slower rates. But each of these, depending on, adds a little bit more to the initial height. So all this stuff in blue is our already finished, we've accumulated this oil. The stuff that's the red rate plus this variable expression, notice t is our variable. So t only appears in the red and black stuff on the right. The rest of it is just some constant that's already done. It's not changing at this point. It's just, it's unpleasant to write it out symbolically instead of approximately in terms of numbers, but each of those blue things is a y initial. All right, so that's it for today. I will see you next time. Let's see.